Okay, welcome to electrical machine lecture. Today we are going to discuss DC motor. Already DC generator discussed, and in the DC generator itself, this diagram we have taken. So the construction, first we will see the construction and working operation of DC motor. So first the construction of DC motor and DC generator is same. So first we will write the construction the construction of DC motor and DC generator is same. When the construction is same, definitely the classification based on the construction of machine will remain same. Now, in case of DC machine, the machine may act as a generator and the machine may act as a motor. Since the construction is same, their part is same, only the difference is that if you are supplying the mechanical input, the machine is going to convert into the electrical output and it is called as a DC generator. So here, the mechanical input or mechanical energy is there in the form of rotation of the conductor under the influence of magnetic field with the help of prime mover. So prime mover will supply the mechanical energy and generator convert that mechanical energy into the electrical energy, then it is called as a generator. Now, if we are supplying the electrical energy instead of the mechanical energy to the same machine, that machine will convert that electrical energy into the mechanical energy and it is called as a motor. So in between there is a magnetic field either for the generator and for the motor. So the first input is the electrical and output is the mechanical. It is called as a DC motor. Since the construction is same, so simply DC machine may be a motor or may be a generator from its operation. This diagram again we have discussed. Here it is the electrical input. This is the input side. And in the input, there are some losses that is called as a copper losses because the current is going to flow into the winding. So I square R loss, this here is nothing but the I square R loss. And there is some magnetic losses are there, leakage fluxes are there and iron losses. Iron losses is due to the eddy current loss and hysteresis loss. The total loss is called as a iron loss. Iron loss due to the magnetic material and it induces some EMF and therefore because of this induced EMF and current does not find external path, so current flows in the form of eddies, therefore it is called as the eddy current loss. Again it is the I square R loss and hysteresis loss. This depend upon the type of magnetic material. Then there is a magnetic coupling, magnetic field loss and total mechanical gross mechanical power developed. After gross mechanical power developed, there are some losses in the form of friction and windage. So if you subtract the windage and frictional loss, from the gross mechanical power output, we get shaft power output. So we will get P out, output power, in the form of torque. So shaft torque is there, or the mechanical power output. So this is the basics of basic concept of DC motor. Now, but what is the working operation of DC motor? We know that when the current carrying conductor, when current carrying conductor is placed in magnetic field, it experiences mechanical force whose direction is given by Fleming left hand rule. Whereas whose magnitude that is the magnitude of force is given by F is equal to force is equal to B L BIL. So BIL in Newton, where I is the current, B is the flux density, and L is the length of conductor. Length of conductor. So it's very simple. When a current carrying conductor is placed in the magnetic field, it experiences a mechanical force whose direction is given by Fleming left hand rule. So in this diagram, again we have taken permanent magnet, north pole and south pole. So the direction of magnetic flux is from north pole to the south pole. Let the current direction as it is given, it is toward us, means the current is coming out from the screen. So we'll see such type of dot. So this is the direction of current. Now stretch your left hand in such a way that your thumb, first finger and second finger mutually 90 degrees to each other. The first finger shows the direction of flux or field, magnetic field. So the magnetic field is from north pole to the south pole, whereas the second finger shows the direction of current. See, this is the conductor the direction of current is out of screen. So see, this is the direction of current. Then the force developed over the conductor, or the conductor experiences the force, is upward direction. So the force over the conductor is upward. So if you just remember the generator diagram, in the generator diagram, the basic diagram for the generator, it has been considered the same diagram. Only the difference is that we are moving the conductor by external force and it induces EMF. So the magnetic field conductor is remain as it is. Only the difference is that we have used the current carrying conductor. We have used the current carrying conductor placed in the magnetic field. Current carrying conductor is placed in the magnetic field, and therefore the conductor experiences the force whose direction is given by Fleming hand rule. And whereas the magnitude of force developed in the conductor is equal to F, B is the flux density, I is the current, and L, this is the length. This is the length of the conductor is there. So this is the basic operation by which the conductor exert force, and if large number of conductor place over the periphery of some cylindrical shape and it is free to rotate, the rotor start rotating, because each conductor are going to experiences force, each conductors experience the force in the same direction. So see here in the second diagram, again this is the north pole and this is south pole. Therefore the flux direction is from north to south. This is the direction of flux. This is the direction of current in the conductor. This is the direction of current in the conductor. What will happen? Now, if you stretch your left hand fingers in such a way that the first finger, second finger, and thumb, all three fingers are mutually 90 degrees to each other, the first finger shows the direction of current and the second finger shows the direction of magnetic flux or field, which is from north to south, as it is shown in this figure B. Definitely, the thumb shows the direction of force is upward. Now, this is the force exerted on this conductor is upward. The magnitude of force is equal to F is equal to I L B. Here the notation just we have changed the direction. So B is the flux density, I is the current, L is the length of the conductor. So this is the length of the conductor. Current I is the current flowing into the conductor, and therefore it produces the force over this one. Now, as we have taken a loop, a two conductor will make one coil. So first conductor and this is the second conductor, right? This is the second conductor. Now the current in the second conductor is opposite to the first conductor. So this is the opposite current. Now if you apply the Fleming left hand rule, in the same way, the thumb shows the direction of force, it is downward. So the same coil, the first conductor will experiences force upward, whereas half of the coil produces the force in the downward. Let you place the number of conductor over the periphery of some circular shape. So see here in this diagram, this is the north pole, this is the south pole. The flux direction is from north to south, whereas the conductor carries current in opposite direction. So this is the current. It is going away. So this is the direction of current, isn't it? So and whereas the 50% means half of the conductor carries current in the opposite direction. So the current in first half, say this half, it produces the force upward direction, whereas the 50% of the conductor under the influence of North Pole produces the force in the downward direction. So this is upward, this is downward, or you can say that this is in this way direction of the forces are there, and hence rotor or this part which is free to rotate produces the torque and run in one direction. So this is the way by which the torque produces in the DC motor. So this is the basic working operation of DC motor. Now, what are the construction? Since the construction feature or construction of DC motor and DC generator is same. That's why just wait for 1 or 2 minutes. So the construction of DC motor and DC generator is same. Therefore, their major parts, they are similar. See, this is the armature. Armature means it is the circular shape, cylindrical shape, where the grooves are made. It is made up of silicon iron, laminated silicon iron, and the grooves carries the armature conductor. It may be one conductor, two conductors, or multi-layers windings are there. These windings and the coils are connected to the commutator segment. Again, the commutator segment is made up of conducting and non-conducting. Copper conducting is the material and mica is there, over which we will place the brushes. So carbon brushes are there in the over the commutator segment. This is frame and it may be called as a yoke, which will serve two purpose. It encloses the rotating and stationary part. It also carries the magnetic flux. Armature winding, the winding which induces EMF, and the winding in case of the DC motor is placed over the rotor. This is the armature winding. The field winding which produces the magnetic flux. These armature windings, this field windings on the poles. So the DC motor may be a 2-pole, 4-pole, 6-pole, 8 poles, and like this one. This is the shaft of the motor, which is connected to the pulleys, and some mechanical loads are there. So this is the some main feature or main constructional feature of the DC motor. So simply the construction of DC motor and DC generator is same. Already the sentence we have written, but again, this is the construction part of the DC motor. Now, as the construction is same, definitely the classification should be same. So this is the classification of the DC motor. So DC motor classified first is the permanent magnet motor, where the instead of electromagnet, we are using the permanent magnet. And nowadays, permanent magnet motors are very much popular in many applications. So this is the permanent magnet motor. Second is the separately excited motor. And third is the self-excited motor. Similar to the DC generator. Separately excited generator, self-excited generator. In case of self-excited DC motor, again there is a classification: DC shunt motor, series motor, compound motor. In compound motor, long shunt compound and short shunt compound. The same classification as the DC generator. Now, with the help of this same one, The DC motor is permanent magnet motor and electromagnet, because we are using electric field, electric current to produce the magnetic flux in the over the periphery of armature. So that's why it is an electromagnet motor. Now in electromagnet motor, the major classification is a separately excited motor. So from this figure, this is the DC motor. It is going to deliver the current outside. The direction, the circuit diagram as it is, only the current direction in the motor is opposite to the direction in the DC generator. So here it is going to deliver the current in the external circuit. Sorry, as it is a motor, so it is consuming the power or current from the source. So we can see this is the direction of current, and it produces the mechanical force. It produces the, say this is the armature, and it produces the mechanical force P mechanical or shaft power. Okay. Now in case of self-excited, again there is a series motor, shunt motor and compound motor. So first, say for example, if you consider the DC series motor, DC series motor. So DC series motor, series field winding and armature. The difference in the generator and motor, instead of G, we will write as a motor. So M is the motor, and this is DC supply. So it will consume the current, but the current direction is from terminal to the motor side. So again, it is a RAC, there is a RA, and it delivers the current. Now, in case of motor, as the conductor rotates under the influence of magnetic flux, it also induces EMF. But the induced EMF is opposite to the supply voltage. Say this is the positive, negative, this is the supply voltage. So it induces EMF whose value may be written as a back EMF. Since the direction of EMF induced is opposite, direction of EMF is opposite, therefore we will call as a back EMF. Since the constructional feature is same, therefore the EMF induced is equal to phi Z N P upon 60A, where the nomenclature is same. Phi is the flux per pole in Weber, Z is the total number of conductor, N is the speed in RPM, P is the number of pole, 60, and A is the number of parallel path. Since the construction is same, the number of conductor, number of poles, P, parallel path is same as that of DC generator. Since the magnitude of EMF, the direction of EMF is opposite. Now let we consider how it will be. Let the rotor is running in this direction. Rotor is running in this direction. Let the conductor having the direction of current. So if you apply Fleming right hand rule to know the direction of EMF induced, say we will take the same example, like this is the current carrying conductor and it is running in this direction. So rotor is running, say for this one, rotor is running in this direction. Now let this is the direction of current, and if you stretch your right hand in such a way that the first finger shows the direction of current, second finger shows the thumb shows the direction of motion, then your second finger shows the direction of EMF induced. So if you apply, this is the direction of magnetic flux. Okay, this is the direction of say this is the direction of force. This will be the direction of current. This will be the direction of current. Now, if you see the direction of current is opposite to the existing current in the armature conductor. So it means that the EMF induced because of the rotation of the conductor under the influence of same magnetic flux, it induces EMF, but the direction of EMF induced is opposite. Whereas the magnitude of EMF is similar to the DC generator because the construction is same. So we have given the name as a back EMF, and the magnitude of back EMF is phi ZNP upon 60A. So from this figure, if you see the equation, we can say that the armature current IA, which is equal to the supply voltage, back EMF, definitely the supply voltage will be more. Therefore, the current is going to flow since the voltage is more and back EMF is small. So V minus EB, this is the difference of voltage divided by the armature current and series field resistance current. So RSE. So this is the current in this. Whereas the voltage V is equal to this. If you apply the Kirchhoff voltage law, V is equal to back EMF EB plus IA into bracket RA plus RSE. Whereas the back EMF is smaller than the supply voltage. So this is the, say, first DC series motor. Now we will take the example of DC shunt motor. So DC shunt motor. DC shunt motor. Field winding. So this is the positive, negative DC supply. Voltage is V. Armature resistance RA. RSH shunt field. It will take the current from ISH. Whereas as it is a motor, so it will consume the current IA and total current is the I. Okay. So from this one, armature current IA or total current I is equal to IA plus ISH. The equation is opposite to the current, isn't it? Because it is, now it produces EMF that is called as a back EMF, whose direction is opposite to the supply voltage. So we can write armature current because this is the terminal voltage and back EMF. So V minus EB upon RA is the armature resistance. R is the armature and this is the current in the armature winding. Whereas the supply voltage is greater than the back EMF. So it is EB plus IA RA. So this is the voltage and current equation in the DC motor. So now same is for the DC shunt motor. The supply voltage is greater than the back EMF. Only in case of long shunt compound generator, long shunt compound motor, armature resistance and series field resistance both are in series, and it the current in the both circuit, both the element is same. So from this one, the supply for the DC motor, therefore the current equation is going to change. In case of DC generator, armature is going to deliver the current in the load circuit as well as the shunt field circuit. Therefore, IA is equal to I plus ISH, but as it is a motor, so it is opposite. So this is the some basic of basic construction, working operation of DC motor and their classification. Next time we will see the back EMF, something more over the back EMF and significance of back EMF in the DC motor. Thank you.